Ladies and gentlemen, good morning. I'm Ariny Demong, currently pursuing my PhD from University Malaysia Sarawak. I'm here today to present my research paper entitled Effect of Swirl Gas Injections on Bubble Characteristics in the Bubble Column. I would like to thank the organizer and all the sponsors to provide me with an opportunity to present my paper. So here is my presentation outline for today. First of all, as we know that bubbly flows mostly occur in most power plants, chemical industries, and refinery industry. So the main purpose of gas-liquid bubbly flow is to enhance the mass transfer between the two phases, which depend on the efficient mixing between the two phases. So the objective of this research is to investigate the effect of swirl bubbles on hydrodynamic characteristics in the gas-liquid bubbly flows. So due to its complex hydrodynamic and transport characteristics, two-phase bubble column has gained high considerations in recent studies. In the gas-liquid reactor, mass transfer between the gas and liquid is the most important goal in the process. So we need to have the effective mixing and high interfacial area between the two phases, which is important to improve the heat and mass transfer characteristics. So as we believe that the swirling flows can increase the mixing efficiency, mass transfer rate of reactant, and thus improve the production rate. So the hydrodynamic parameter includes the gas hold up, bubble size, and liquid circulation velocity, which relate with the volumetric mass transfer. So these hydrodynamic characteristics depends on the flow regime occurred in the bubble column, relatively low superficial velocity, small bubble traveling to top of the column with the little interactions among them is referred as homogeneous bubbly. So that there are few parameters that need to be considered to design the bubble column reactor, such as specific gas-liquid interfacial area, axial and radial dispersion coefficients, bubble diameter, mass transfer coefficients, gas hold-up, and physiochemical properties of the liquid medium. So at a point where gas is injected into a standard liquid, bubbles are formed and rapidly move upward to the buoyancy force. The bubbles are formed by the breakup of the bigger bubbles. So there are three components cause bubble to break up. For example, instability of larger bubble, detaching the edge of larger bubble, and collision between bubbles. Besides that, bubble size also can be increased through the collisions, which two or more bubbles are coming together. There are three mechanisms of bubble collision, such as bubble collapse through because of turbulence, different bubble size towards each other, and one of the bubble being drawn into the wake of preceding one. So next part is methodology. As you can see from this figure 2, it shows that the bubble column experimental setup. So these investigations was carried out in a bubble column with a diameter of 57 cm and 61 cm in height. So it consists of a column made of plexiglass was equipped with the ring sparger. So the liquid used was tap water and the gas phase was air from the air compressor. So this experiment will perform at gas flow rate range from 0.063 gram per second to 0.316 gram per second. So this technique are high-speed cinematography, conversion of bubble image into data structure, tracking of multiple moving bubbles, bubble trajectory reconstruction, and bubble velocity measurement. So figure 5 shows an image processing of cluster bubble to form an individual bubble. So based on the area of the regions, the bubble are divided into spherical bubbles, intermediate size bubble, and large bubble or cluster. So thus a multi-level segmentation approach is suggested to extract the maximum possible information from the image. Image segments of the bubble are created by group of bubbles and not by individual bubbles, such as when two or more bubbles are overlapped in the image, they are detected as a large single bubble. This caused an error in measuring the size and velocity distribution of the bubble. However, the overlapping bubbles recognition technique is applied, which only measure the in-focus bubble and remove the bubble shadow, as shown this figure 5. So next is result and discussion. So in this result parts, the bubble characteristics such as bubble size, bubble population, and bubble velocity was studied to investigate the effect of swirl gas injection as we vary the inlet gas flow rate and spiral rotation speed. Okay, so this figure 6 shows the image of bubbly flow when the gas is injected into the column. Visual observations indicate that the bubble size has decreased from 10 mm to 2 mm with an increase of impeller speed over the range from 0 rpm to 150 rpm. So by increasing the rotation speed of sparger, the bubble move vigorously, thus making the regime more dispersed, and bubbles move in zigzag motions due to the increased water circulations in the column. However, by increasing the gas flow rate, the bubbles begin to grow in size and large bubbles appear to coexist with the smaller bubbles as shown in figure 7. The uprising bubbles begin to exhibit also a reciprocate movement which retard their upward movement, enhancing the collisions. So increase in gas flow rate injection into bubble column, the coarser bubble are immediately released from the sparger's hole because of high buoyancy, and the bubble face more resistant to move in upward directions as well as high residence time in the column. So this resulting in more mixing caused by the interaction of phase and hence increase in mass transfer as well as the turbulence in the column. So for figure 8, it shows that the effect of the sparger rotation speed on bubble column. So as we increase the rotation speed from 30 to RPM to 150 RPM, you can see that the bubble populations also has been increased. Besides that, the increase of bubble also reduced as the rotation speed is increased. As the rotating sparger increased to 150 RPM, the bubble size reduced from 12 mm to 4 mm. So the uniform bubble size distribution of small bubble may increase the gas hold up and gas transfer area in bubble column. So the populations of the bubble is higher as the sparger rotation speed increase due to the formations of the bubble is more uniform, which there are more of smaller bubbles. Besides that, the size of the bubble also reduced as the rotating speed is increased. Furthermore, figure 9 shows the bubble rising velocity affected by the bubble size, where the result from this work agreed well with the literature for air-water system. The bubble rising velocity increased as the bubble size increased for conventional gas injections. A large bubble has high rising velocity because larger bubble has the larger buoyant force compared to the smaller bubble. So at constant gas flow rate, by increasing the rotating speed from 90 to 150 rpm, the average bubble velocity reduces as the velocity is easily dissipated to the surrounding far from the center region of the bubble column. So last but not least, come to the conclusions part. The swirling bubbles can enhance the mixing between air and water as well as giving the larger dispersions of bubble in the air-water system. So from this study, we can conclude that the efficiency of the air-water mixing is increased, thus give knowledge that by inducing swirl bubble in the flow, we can enhance the performance of the bubbly flow rector. So this is the different references. Thank you for listening to my presentation.